Alright guys, welcome to lesson 4. We're going to learn yet another derivative rule, as we will in Unit 1 repeatedly. For this particular lesson, we're looking at something known as the quotient rule. After that, I'm going to introduce you guys to something called higher ordered derivatives. So we'll talk about what that is when we get there. But those are our two objectives for this lesson. So here's the quotient rule. So what is a quotient? Well, quotient means division, which basically is just in algebra expressed as a fraction. So in this case, I have a function which is defined as a fraction or a quotient of two other functions. So whenever you have a function that's defined as a quotient like that, we're going to use the quotient rule if you want to find the derivative. Now here it is. It looks really ugly, but there's actually a really cool little rhyme that goes with it. So I picked the letters of these functions on purpose. The H stands for high. The L stands for low, for obvious reasons, right? I call the H the high one because it's on top, and I call the L function the low one because it's on the bottom. So I want to share with you guys a really neat way to memorize this particular derivative rule. It's a little rhyme. It goes like this. It's low d high minus high d low, draw a line and square below. Low d high minus high d low, draw a line and square below. So this is the quotient rule. So you do the low function multiplied by the derivative of the high function minus the high function multiplied by the derivative of the low function. Draw a line and square below. So there's your rule. So low d high minus high d low. Draw a line, square below. So this is the quotient rule. This is a little formula that somebody figured out, and we will later on in the year figure out where these little rules come from. They're not just made up, they actually are derived in a certain way using logic and mathematics. But for us, we're just memorizing them for now. But this is a formula that could tell you the slope or the derivative, or in other words, the instantaneous rate of change of a function that is a quotient at any point. Okay? So let's go ahead and see if we can bring this to life a little bit with an example problem. So we're going to start off with another table problem here. So given that h is equal to f over g, find h prime of 3. So the first thing we need to do is we need to find the derivative of h. Now since h is a quotient function, if I want to find its derivative, I need to do the quotient rule. And for the quotient rule, we have a nice little rhyme to go with that. It goes like this. Low, which is g, d high, which means derivative of the top function, minus high, d low. Draw a line, which I've already done, and square below. So there is my quotient rule. After you find the derivative, that's the formula that can tell me the slope of the h function at any point. Now I want to actually find out what is the slope. What is the instantaneous rate of change of this function when x equals 3? So now I'm going to go ahead and plug in 3 to the function for the derivative. After this, you guys know it's all about just getting your stuff out of the table and simplifying it. So here we go. G of 3. G of 3 is 1. Next one. F of 3, or F prime of 3, I should say. That's 0. F of 3, F of 3 is 4. finally, g prime of 3 is 0. Well, actually, not finally. We need to do the bottom now. G of 3 is 1, and that's being squared. So we have 0 minus 0 on the top, which is 0, over 1, which is 0. So there's our final answer. The slope of the h function at x equals 3 would be 0. It would be a flat slope, a horizontal line. So in other words, the h function would probably look something like this, because the instantaneous rate of change, which is the slope of the tangent line at that point, would have to be flat with a 0 slope, which means that it would probably be like either at a maximum or it could be at a minimum value of the function, the bottom or top, where it curves. But I'm just adding a little extra information there. You don't need that for now. So here's one for you. This table looks similar to me to the other one. I think it is the same table this time. But all that's different is you're plugging in a different number. But if I were you, without looking at the last example, see if you can accurately write what the derivative of h is without looking, and just using that little rhyme. Low d high minus high d low, draw a line and square below. Okay? So I'll go ahead and pause the video there, and when you unpause it, I'll have the solution up for you. Okay, so here is the quotient rule. And now I want you to go ahead and do the next step where you plug in your given number. And go ahead and simplify it as much as you can. You'll come across something interesting there, and we'll talk about it. So go ahead and pause the video there, and when you unpause it, you'll see the rest. All right, so you guys should have gotten up to here okay. And now we want to figure out what to do about these fractions up here. This happens sometimes. In this case, you would just want to think of this as 2 over 1, right? And then you could either do top times top, bottom times bottom, in which case you're going to get 6 over 2. And then you would just reduce it. Or in this case, actually, you can cross-reduce and just end up with 3. Same thing over here. The 2's are going to cancel, and you're left with 3. But this time it's a negative 3 that's left over. On the bottom, we have 4. And hopefully you guys recognize that double negatives make a positive. So we actually end up with 6 over 4 as a final answer there, which is 3 over 2. Okay, so that would be our final answer for this particular problem. Now, what was beneficial about this problem is that even though we had fractions, they kind of just cancel out and reduced. You actually can be left with a fraction up here after that, though. And there are ways to handle it, but we'll cross that bridge when we get there. But for now, that's the end of that one. All right, next problem. Another example of how to use the quotient rule. So we just did an example that involved tables, but let's go ahead and do an example that involves equations, an actual function this time. So how the quotient rule works is if I want to find the derivative, it's going to be low d high minus high d low. Draw a line and square below. Okay? So what goes here is the low function. So my low function is 5x squared plus 2. What goes here is the derivative of the high function. Low d high, right? So d high, the derivative of the high function, the derivative of that would be 15x squared. So low d high minus high d low. The derivative of the bottom function, or the low function, would be 10x. Draw a line and square below. Square the bottom function. There you go. Now we can just leave it like that. That would be totally fine. We don't need to simplify it anymore. It just kind of makes things unnecessarily complicated to do that, so we'll just leave it like this. Okay. And there you guys have it. That is the quotient rule. All right, so let you guys try one of those. Once you guys give this one a shot, pause the video. When you're undone pausing it, the answer will be up for you. All right, there you guys go. That's what you should have gotten for student practice 2. Moving along. Okay, so let's go back to an example about cars. We've done that earlier this semester. So let's say that this was miles. No, I'm sorry, this would be, yeah, miles. We'll call this axis the miles axis. We'll call this the hours axis. And this person must be driving across country or something because they're driving a long time. Okay, so let's say that they're driving, well, I guess I'll just make some stuff up here. I'll just go by 50s. Okay, so let's say at 0 time they've gone 0 miles. After 1 hour they went 50 miles. After 2 hours they went 100 miles, and so on. And that's just going to keep going, obviously. We end up with a straight line there. So what would the equation of this line be? Well, first of all, it's a straight line, so we know it has this form, right? We know that the B represents the y-intercept, which in this case is 0. We know that this M represents the slope, so that would be the rise and run. It's going over 1 hour and up 50 miles each time, so it's 50 over 1. And there's the equation of that line. Now, what is the speed of this car? The speed of this car is 50 miles an hour, right? Every hour, it goes up 50 miles. And that's the slope, right? But what's the derivative of this equation? Well, using the constant multiple rule, it's 50. And we've been talking about this, how slope is the same thing as derivative, is the same thing as instantaneous rate of change. And when you're talking about a car, it often represents speed. Now, later on in the year, we'll talk a little bit more about this. It actually doesn't represent speed so much as it represents something called velocity. But if you haven't had physics yet, I don't want to confuse you. Speed is good enough for now, okay? So the derivative tells you the speed of the car. Now, I'm going to change the story a little bit, though. This is what the graph looks like if the car is always driving 50 miles an hour. But let's just say that let's change the story a little bit. Let's say that instead of doing miles and hours, let's do seconds. Let's say these are seconds now, just to kind of try to keep this story I'm about ready to create a little bit easier. And let's say that these now represent maybe I don't want to have to change all these numbers, so I'm going to go ahead and say inches. Okay, so let's say we're on a bicycle now, and after every second you're going 50 inches. I don't know how realistic that is. I tried to make it realistic, but there you go. But now let's say something else happens when you're on this bicycle. Let's say that you just came to a cliff. Well, what's going to happen when you get to the top of a mountain and you just kind of start coasting downward? What's going to happen is you're going to do what's called accelerate, right? And what does that mean? What is acceleration? Acceleration means that your speed is increasing. Actually, it could also mean, we don't usually use it this way in English, but in physics and mathematics we do, it can also mean that your speed is decreasing. So really a better way of saying it is that acceleration is your speed changing somehow. Now let me ask you guys a question. If this is our graph for our bicycle going 50 inches per second, if we all of a sudden get to a hill, my graph won't look like this anymore. Can you visualize what the graph will look like if we start coasting down a hill? At first, after the first second, maybe you will just be going 50 inches per second. But after another second, you start to go a little bit faster. So after the second second, instead of going 50 more, maybe you went a little bit more than that. And then by the time you get to the third second, instead of going a little bit more than 50, now maybe you're going maybe twice as much as 50. And so on. And so what happens is your graph starts to bend. Okay? Instead of being a straight line, it starts to bend. And that demonstrates that your graph has an acceleration to it. So you can tell a function has an acceleration. In other words, you can tell the speed is changing anytime the line is bending. Okay? Now, but here's another interesting thing here. What we had up here before, let's go back to this. This was an equation that represented after a certain number of seconds went by. If I multiply that by 50, that will tell me how far my bicycle went. And when I took the derivative of that, that told me how fast my bicycle was going at any point in time, right? But if your speed is changing, well, then that means that your speed has a slope too, right? Anytime something is changing, it has a rate of change. So if speed is changing, because it's accelerating, then speed has a rate of change, or a slope to it. Or you could say it has a derivative. Or you could say it has well, I guess we already have that one, right? Instantaneous rate of change. All right, so anytime you have a bending graph, not only does it have a derivative, which tells you how fast the graph is changing at any point in time, but it also has a derivative of the derivative. In other words, it has an acceleration. Okay? Now, let's go back to our straight line story, though, for a second. It looked like this, right? There was the equation. The speed of the bike or the car, whatever you want to think of it as, was 50, right? 50 inches per second or 50 miles per hour, whichever story you're thinking of. What happens if I take the derivative of the derivative? In other words, I'm going to take this derivative.
Mr. Bailey.
So you guys will notice that I put another little prime mark there because I'm taking the derivative of a derivative. Now, this was a constant. What's the derivative of a constant? It's 0. So what this tells me is that if you have a bike that actually is going at constant speed, then it doesn't have an acceleration. Its acceleration is 0, right? So what I'm trying to communicate to you guys here is that basically, if you have a function that represents position, right? Let's say we have a function that represents the position of that object, then f prime, the derivative, would represent speed. The second derivative would tell you how fast your speed is changing, which is acceleration. Okay? So the point I'm trying to make across is connecting this to real life stuff, is the fact that you can have a derivative of a derivative. And that leads us to the concept of higher ordered derivatives. So we've been talking so far in this class about the first derivative, and here's all the ways to write that. But you could take the derivative of a derivative and get the second derivative. These are all the ways to write that. So if you're using the prime notation, you just put 2 primes. Okay? However, when you're doing the dy dx method, something is kind of interesting here. Notice we have 2's, right? That makes sense because we're talking about the second derivative. But do you know something funny about the way that those 2's are placed? On the top, the 2 is between the d and the y, and on the bottom, it's next to only the x. Now, I'll explain that in a minute, but for now, just notice that because that does matter. And if you don't write it correctly, then on a free response question, that actually would cost you points. The reason being is because if you don't write it like that, you would actually be writing something completely different. It would mean something else. You can even take the derivative of a derivative of a derivative. You could do that a third time. As a matter of fact, you could do that as many times as you want to. Okay? So you can take as many derivatives as you want to. Going back to our example, if f represents position, f prime represents speed, this represents acceleration, there actually is a meaning to this. It's called jerk. Now I'll try to explain why they call it that. It's not because it's a jerk. It's mean. It's rude. They call it jerk because it feels like a jerk. Like whenever you're in your car and somebody jerks the wheel really fast and you feel that weird jerk, that they call it that for that reason. So imagine that you are in a car, and imagine that your friend is accelerating the car. So the speed is getting faster and faster. You feel acceleration at that point, don't you? What acceleration feels like is it feels like you are being pressed against the back of your seat, right? But what happens if he slams on his brakes? Well, you were going faster and faster, but all of a sudden you started changing your acceleration. Now you're not going faster and faster anymore. Now you're going slower and slower. What does that feel like when he slams on his brakes? That feels like a jerk. So when you change your acceleration, it's called a jerk. Okay, and that's a physics concept which you might talk about if you get into physics. We don't talk about it too much in here, but I just thought it'd be an interesting thing to mention. After jerk, I really have no idea how that would connect to real life, so I'm just going to leave it off. But there it is. Now let's talk about this notation a little bit. Why does it have to be written like this instead of like this? Why do we write it like this and not like this? Well, let's explain why that is. It actually makes sense if you think about it. So, suppose I have a function, and I want to take the derivative of this function. So I'm going to take the derivative of y, and what that's going to give me is dy dx, right? Now, here's a neat thing about this notation, and when you write it like this, it kind of works like fractions. So you can think of this as y over 1, and even though we're not multiplying, it works like multiplying. So you could think of it as like d times y is dy, and dx times 1 is dx, right? So keep that in mind. This is taking the derivative, and it's kind of, you follow the same steps as multiplying, even though you're not really multiplying. You're finding a derivative. It's very different. It's just that the way the symbols work is similar. Now I want you to watch this. So now suppose I want to take the derivative of my derivative. So here's my derivative, and I want to take the derivative of that. Well, if I take the derivative of that, wouldn't that be d times d, which is d squared y, over dx times dx, which is dx, and we could put parentheses squared. So really when they put dx squared here, you're not squaring the x, you're squaring the whole thing. Okay? So that's why it's written like that. So if you were to write it like this, let me back up a little bit. If you were to write it like this, you know what that means? That means this. Now in this case, this literally means you're taking a derivative and you're multiplying it by itself. That is a very different thing than taking the derivative of a derivative. So even though the notation kind of works similarly, they are different concepts. So it's important you don't write it like this, and it's important that you do write it like that because they mean different things. This one means squaring the first derivative. This one means taking the derivative of the derivative. All right. So that being the case, there's your higher order derivatives. So let's go ahead and take an example here. This says y equals x to the fourth, and they're asking us to find y triple prime. That means they want us to find the third derivative. So here we go. If y equals x to the fourth, then y prime would be, move the 4 to the front, and take 1 off the power. It's a power rule. And that's y prime. Now if I want to find the second derivative, the acceleration function, repeat. Multiply the 3 times the 4, and take 1 off of the power. And if I want to find the third derivative, which is where I'm going to stop, because that's what the problem asked us to do, was to stop at the third, you're going to multiply the 2 times the 12, and take 1 off the power. And there you go. There's your third derivative. All right. Now, let's go ahead and take a look at number 2 here. Now, for number 2, they want us to find the second derivative, as you can see here. Now, what kind of a function is this? Y is a special kind of function. What kind of a function is that? Now, some of you guys might say, oh, it's quadratic. Well, that's nice. That's true. That's not the word I'm looking for, though. It's a word we've talked about this semester already. So what kind of function is this? Well, this is a product function. I have two pieces of functions being multiplied together. So if you want to find the derivative, then you need to do the product rule. So let's find the derivative. The first derivative is, okay, now we get to remember how to do product rule. It's different than quotient rule. It's blank times blank plus blank times blank. AB, AB, prime, prime. Okay? So we're going to call the first one A, the second one B. A prime is 1. B prime is x plus 3. A is x minus 3. B prime is 1. Multiply. And there's my dy dx. Now if you want to find the second derivative, we take the derivative of this. So the derivative of x is 1, the derivative of 3 is 0, the derivative of x is 1, and the derivative of negative 3 is 0, and we end up with 2 as our final answer. Now, that's not the only way to do this problem. Some of you guys might have found another way to do it, okay? But this is one way to do it. Now, some of you guys might have been a little sharp, a little on your game, and you might have noticed something. Mr. Bailey, I recognize that. My teacher last year told me that this is something called the difference of squares. So if you were to multiply these, you actually just get x squared minus 9, and I remember that. So I'd say, okay, cool, good obs. That's actually going to save you a little bit of time. So if you start by rewriting this as x squared minus 9, then when you take your derivative, it's easier. You don't have to do the product anymore. You just can do the power rule. The derivative of x squared is 2x, the derivative of 9 is 0. And then when you do your second derivative, you get 2. So we're learning so many rules, it kind of gets to a point where you guys actually have various options for how to do things. Okay? So on this one over here, we did the product rule. Over here, we just had to do the power rule twice. All right. So here's some student practice for you guys. Go ahead and do numbers 1 and 2 here. Pause the video. When you unpause it, you'll see the solution. Okay, so here's your answers. Number 1, you guys should have just gotten 0. First derivative is 9, second derivative is 0. For number 2, the first thing you should have done, you should have rewritten the problem with a power as exponent instead of the radical. Notice that it's still y, though. I didn't make it y prime, right? Rewriting it is not a derivative. It's just rewriting it in a different way so that we can do the derivative rule, right? So it's still y. And then after that, I do the first derivative, which is a power rule. So I multiplied the 3/4 to the front and took 1 off the 3/4, and I got negative 1/4 for the new power. Then we do the power rule again to find the second derivative, because we're trying to get to the third derivative, right? So the second derivative, you're going to multiply negative 1/4 times 3/4, and that gives you negative 3/16. And if you subtract 1 from negative 1/4, you end up with negative 5/4. Now, for those of you guys that forgot how to do it, this is the long way to do that and get a common denominator, right? But the fast way is just to subtract the bottom number from the top. So negative 5 minus 4 is negative 9. Or actually, I think I'm doing the wrong one. Let me back up a little bit, sorry. We're doing this one. So we want to subtract the bottom number from the top number. So negative 1 take away 4 is negative 5. And just keep the bottom number the same. So that was our shortcut that we learned. And then since we want the third derivative, we need to do the derivative one more time. So we're going to multiply negative 5/4 to the front. Negative 5/4 times negative 3/16 gives me 15/64. And taking 1 away from the power there gives me negative 9/4. So that, you could stop there. But don't forget, there are ways to rewrite it, right? As you guys know, I forgot a prime there. As you guys know, when you take a derivative and you end up with a negative power, you can put that expression in the bottom so that it has a positive exponent instead. So I can move the x to the 9/4 to the denominator with the 64. Another thing you can do to write your answer is you can actually write it back as a root again. So the 4 is a root, then we have x and then 9. Okay? Now I'm going to show you some more stuff, but honestly, your answer will either look like this on your multiple choice test, or it will look like this. It will probably look like this, but it's possible that this would happen. This is just kind of like, if you're going to go farther than this, you might as well go all the way, right? But now I'm going to make it even more complicated. And it will not look like this on your multiple choice test for my class, but it could be on like a AP type question thing. And it's not calculus, it's just more old school math. They might actually ask you to simplify this a little bit, because you can. Do you guys remember how to find the 4th root of a number? Well, x to the 9th means you have 9 x's in there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And a 4th root means you're looking for groups of 4 things that match. So for every group of 4, you can cross that off and put an x on the outside. So actually, this is x squared multiplied by the 4th root of 1x is left inside. So another way you could write this would be like that. Okay. All right, I think I'll stop there. There's actually even more things you could do to rewrite this, but I think I'm going to stop there because I just don't see them going that crazy with it usually. But just stretching your guys' review a little bit there, making you think a little bit. All right, and that concludes our lesson on the quotient rule and higher order derivatives.